All right, let's go over the last questions. First, you aren't too long, though they can be a little confusing. So we've got this small box on the ramp. We got friction force, we got gravity, we got some pushing or pulling force, and normal force. And we got to figure out which free body diagram works for the given situation. If it's accelerating up the ramp, we're going to need some pulling force. It would have some friction force. Mg would be straight down, and normal force is straight out of the surface. So yeah, it would just be E. Not too bad given that it's accelerating up and there's only one where you've got a net force up that is not caused by friction. Friction's probably not going to pull it up unless it's on a conveyor belt or something. Which figure best represents the free body diagram for the box if it's at rest on the ramp? So if it's at rest on the ramp, all the forces got to cancel. In that case, it would be C here. It wouldn't be D because a real free body diagram, like you'd put on a test, does not include components. This guy includes components, so it is excellent for your purposes, except actually it's got these guys backwards. So this guy should be mg sine theta, and this should be mg cos theta. So that's a bit of a giveaway. But anyway, if you're submitting a question, you do not want to include components. So it's not D. It's going to be C. And now here's the kind of confusing part. So that was when it was at rest. What if it's moving at constant velocity? What if it's sliding down the ramp at constant velocity? Well, again, if it's at rest, your kind of upslope forces cancel with your downslope. But if it's going at constant velocity, it's the same situation. At rest is kind of like a special case of constant velocity. It's constantly zero. But either way, all your forces got to cancel, and it's going to look like C. So same answer twice, just to throw you. All right, number 24. You got two blocks of masses M and M, with M is bigger than M, connected by a light string. The string passes over a frictionless pulley of negligible mass, so the blocks hang vertically, and they're released from rest. So basically what you got is you got this situation. You got like a big M, and you got like a little m, and you're going to use big minus small. So we got big minus small equals ma, and we're going to solve for a. Big is the force of gravity on the big mass, so mg, and minus the force of gravity on the little mass. And this m is the mass of the system, because we're doing big minus small for a whole system. So that's going to be our total mass for the whole system, and then we get the acceleration of the whole system. It's all tied together, so finding the acceleration of mass m is the same as finding the acceleration of the whole system. So anyway, if we rearrange it, we got big mg minus little mg all over m plus m equals a. And if you look at which one is equivalent, it's going to be this sucker. It's just a factored out the g. Same thing. I kind of love these horizontal blocks against walls sort of questions. Make you think a little differently. So we want to know how hard we got to shove this block into the wall so it doesn't slip. So best way to deal with something like that is a free body diagram. So if we think about it, we got this big force into the wall. We got our normal force out of the wall. Remember, normal force is just force exerted by a surface straight out of itself. We got gravity straight down, and you might be like, what's holding it up? And what's holding it up is friction. Friction is always along the surface, and it opposes the tendency to motion. Along the surface, in this case, is up, and it's tending towards down. So there you are. So if we want to know what F is the same as Fn. And I would start off with mg equals F. But F is just equal to mu Fn, right? But Fn is just F. It's equal and opposite to F. They're canceling each other. So what are we trying to solve for? We're trying to solve for f, so it's just going to be mg over your coefficient. And if you free body diagram and just start with your kind of up equals down, your gravity equals your force of friction, it sort of follows, and the fact that your normal force is equal to the applied force. All right. So we got a dart gun used to fire 2 rubber darts with different but unknown masses. We got the same force in each dart, but we don't know how big that force is. We know the accelerations, or we measured the accelerations of both darts, but again, we don't know their mass and we don't know the applied force. What can be determined from this data? Really, we can't solve for F because we don't have M, and even though we have A. We can't solve for M1 and M2. To do that, we need the force. If we had the force, we could easily solve for M1 and M2 just using F net equals MA. But what we can do is we can solve for the ratio of M1 and M2 only. So if one of them accelerates twice as fast, it's half the mass of the other guy. So the ratio of the accelerations is kind of like opposite the ratio of the masses. If that makes sense. Again, if one is, just think through, hey, if one of the accelerations was double the other guy, you'd be able to tell, let's say A2 was accelerated twice as fast as A1. That would mean M2 was half the mass of M1. So think that through. All the other things we just don't have enough information for. 27. Velocity of an elevator moving upward between adjacent floors is shown as a function of time. Which of the following times is the force exerted by the elevator floor on a passenger the least? I would say the force exerted by the elevator floor on the passenger would be the least if it's moving upward when it's slowing down. Because you think about it, you're at a floor, you accelerate up. So when you're accelerating up, the floor has to push up on you enough to fight gravity and to start you accelerating up. And then you reach kind of like a constant cruising velocity and you feel pretty much as heavy as normal. The floor is pushing on you like just enough to fight gravity. But then you start slowing down for your floor. And then at that point, while it's slowing down, it wants you to accelerate down. You had a bunch of upward velocity and you want to lose it. So the floor doesn't push on you as hard as it needs to fight gravity. It pushes on you a little less than gravity, and that causes you to accelerate. And it goes from 4 meters per second up to 0 meters per second. So it would be probably around 6, where your slope is the greatest. All right, so 28. We've got an object mass m moves with an acceleration a down a frictionless incline that makes an angle with the horizontal as shown above. If n is the normal force, which of the following is correct? I think it's just a equals g sine theta, which is kind of silly. Anytime you got a frictionless incline, this is always true. It's not a bad thing to memorize, because basically if your net force is your perpendicular or parallel force, that means that MA is equal to mg sine theta. Cancel out the m's and you got that sucker. So there's a bit of misdirection. It's like, what if n is the normal force? Well, yeah, it doesn't matter. N won't be mg, it'll be mg cos theta. It'll be equal and opposite to f perpendicular. The normal force is certainly not the net force unless it's being launched like straight out of the surface. So yeah, just that. 29, we got this skier slides at a constant speed down a slope, inclined at an angle of phi to the horizontal shown above. Air resistance is negligible. The coefficient of friction mu between the skis and the snow is equal to what? So big key is we got constant speed. So basically your downslope forces equal your upslope. In your downslope, you got your F parallel, and your upslope is friction. So you got sort of mg sine theta. Love your little triangle. Whee. F perpendicular equals, this is mg, this is phi, mg cos. Sorry, I ran out of space again. Yeah, and your F parallel is mg sine phi. Since force of friction is mu Fn, and Fn is equal and opposite to this F perpendicular, we got mu mg cos phi. This is phi, not theta. Cancel out our m's, and then we want to find the coefficient of friction. So we just divide both, or we can cancel out our g's too. So our coefficient of friction is just sine phi over cos phi. Which hopefully you know is the same as tan phi. So there we are. Not so bad. All right. Let's do the 31 and 32. So we got a 5 kilogram object propelled from rest at time t equals 0 by a net force F that always acts in the same direction. The magnitude of F in newtons is given a function of seconds by F equals 0.5 t. Speed of object is t equals 4 seconds. Again, much like previous question, the one with the graph, we have the same two options to solve for it. This guy. So remember with this guy, we could either find like average force and do average force divided by mass equals time, or we could do kind of like area under it. Area under it is the same as integral. I'll do the integral just to get you used to it. So basically use an integral anytime you'd want to find the area under the graph. If you've got one of the things is changing with respect to the other, so in this case force is changing with respect to time, we could take the integral of it. If something's multiplying, we can take the integral. So like F times t is equal to m delta v. But m delta v, or change in p, which is the same thing, is also equal to the integral of force with respect to time. So that's what we're going to do. So we're going to say, hey, integral of force with respect to time is 0.5 t dt. Integrate that. We will increase our exponent by 1 and then divide by the new exponent. So that's going to equal t to the 2, and then 0.5 over 2, we got 1 over 4. Just do t squared over 4, plus a constant if we want, but it was propelled from rest. And so it was propelled from rest, the constant is just 0, because that's kind of would be our initial momentum. But our initial momentum is told to be 0 because our velocity is 0. Anyway, we want to know how fast it's going at time t. So we got kind of like m delta v equals t squared over 4. So we just divide by 20, I guess. Or sorry, m is 5. So our change in velocity, is just 16 squared because we're looking for the thing at 4 seconds. Or sorry, not 16 squared, just 16, 4 squared. 4 squared over 20 is 5 times 4 is 20. So we've got 16 over 20, which is just 0.8. And then the last guy, car traveling along a straight level road when it runs to gas at time t equals 0. From then on, the net force is a resistive force of minus kV, where v is velocity and k is a constant. Again, just make sure the slope is what it should be. The slope depends on the velocity. So initially, our velocity is high, so we're going to have a pretty steep slope, right? Because we're going to have a pretty big acceleration or a pretty big net force on it. So our slope should initially be quite steep because the higher velocity, but as our velocity approaches 0, our slope should approach 0. So it's got to look kind of like this. Though of course this is wrong, so that's not it. Our position, we're moving forward and we never move backwards. So we're initially moving forward quite fast, initially quite a steep slope, but then it gets less and less with time. So we just need to make it match. So position graph that looks like that, a velocity graph that looks like that. So answer is D. And thank you for listening.